Excellent. If this is my clue, then thank you very much, Piers. My name is Gergely Zimanyi, and I will be the session leader for this roundtable discussion entitled, "What key roles can ICAM scientists play in the era of climate emergency?" We have a very distinguished panel. Ben Center joins us, who for decades played an absolutely central role in the intergovernmental studies on climate change. And very recently, we just learned retired from Livermore. And we have back with us Eli Jablanovic, who has been a sensational actor in this field. One of the things what I admire Eli a whole lot for is that he is co-founder of a company called Alta Devices, which holds the world record in conversion efficiency of solar cells. So this is the panel. I believe that this will be a relatively loose format, so please feel free to step in and ask questions. Loosely speaking, the panel format will be that first Ben, then Eli, and then finally I make opening remarks on the scale of 10-12 minutes, and then we open the floor for a discussion. Having said that, Ben, take it away for your opening slides, please.
Thank you very much. Can everyone see my slides?
Yes.
I can.
Yes. So just a few introductory remarks about climate change and how physics and physicists have contributed to advancing our scientific understanding. So Gergely mentioned the IPCC, the Intergovernmental Panel on Climate Change. They've been around for well over 30 years now, since 1988. And their role is to advise the governments of the world what we know about the physical climate system, what we know about the impacts of human-caused climate change on stuff we care about. Think agriculture, energy resources, water, human health, ecosystems. And there's also a branch of the IPCC Working Group 3 that considers mitigation and adaptation options. The first report of the IPCC was published in 1990, and essentially it concluded that the jury was out in terms of the causes of climate change, that we didn't know enough in order to determine definitively whether there was a human-caused warming signal or not. The second assessment report was published in 1995. I was the convening lead author of the detection and attribution chapter. And after 1.5 years of work, our group of scientists around the world came to this 12-word conclusion: the balance of evidence suggests a discernible human influence on global climate. And it was the first time that the international scientific community said, signal detection in our time. We formally have identified a human-caused warming signal. That was controversial 26 years ago. It led to a lot of unpleasantness, congressional investigations, calls for my dismissal with prejudice from my position at Livermore. And I learned a lot of important lessons through that experience. But the third assessment report, conducted by an independent group of scientists and published in 2001, went far further than our cautious balance of evidence finding and tried to quantify the size of the human effect on climate, famously concluding that most of the observed warming over the last 50 years was due to human activities. There were subsequent reports in 2007 and in 2013. Those went further than the 2001 report and used this likelihood language to try and get at the probability that indeed a human-caused warming signal had been detected. And most recently, just a couple of months ago, the sixth assessment report concluded that it was unequivocal, their word, that human influence had been detected not only at Earth's surface, but in the atmosphere, in the oceans, human fingerprints were pervasive. And part of my story is that the physics community has played a role in advancing that arc of understanding. One of the very influential contributions from the physics community was through this gentleman here, Klaus Hasselmann, the former director of the Max Planck Institute for Meteorology in Hamburg in Germany. I had the extraordinary privilege of doing my postdoc with Hasselmann in 1987 through to 1992. Hasselmann's share of the Nobel Prize for Physics in 2021 was for, quote, developing methods for identifying specific signals, fingerprints, that both natural phenomena and human activities have on climate. And one of his key insights in a paper published in 1979 was that we need to interrogate patterns of change, either geographical patterns or altitudinal patterns through the full vertical extent of the atmosphere, or patterns through slices of the ocean. Up to that point, 1979, scientists who were interested in signal detection had looked at individual locations, grid points on the Earth's surface. They hadn't interrogated the entire global scale pattern of climate change. And Hasselmann's insight was that, say, the pattern on the left, the warming of the lower atmosphere, the troposphere, in response to human-caused greenhouse gas increases, was large scale. It showed warming everywhere, larger warming in the northern hemisphere, particularly over the Arctic, due to feedback mechanisms associated with the retreat of snow and sea ice. Whereas the dominant patterns of unforced natural climate variability associated with things like El Niños and La Niñas were not uniform sign everywhere. They were smaller in scale, spatially much more complex. And Hasselmann's advice to me as a young scientist and to the entire field was use this pattern information to try and discriminate between signal, human-caused warming signal, and noise. So we did. Enter this gentleman, another very prominent physicist, Suki Manabe from the Geophysical Fluid Dynamics Lab in Princeton, also one of the co-recipients of the 2021 Nobel Physics Prize, which in Manabe's case was for the physical modeling of Earth's climate, quantifying variability, and reliably predicting global warming. My scientific career also intersected with Suki Manabe. Back in 1967, Suki and his GFDL colleague Dick Weatherald published perhaps one of the most famous climate science papers ever. And what they did is they used a very simple so-called radiative convective model with atmospheric convection in there. And they increased atmospheric CO2 from 150 to 300 to 600 parts per million. And when they did that, they found that the lower atmosphere warmed, the troposphere, and the upper atmosphere, the stratosphere, cooled. Heat was more effectively trapped lower down in the atmosphere, and the upper atmosphere had to cool in order to restore radiative balance. Now, this was 1967. It was a true prediction. We didn't have the satellite temperature measurements to determine whether Suki Manabe and Dick Weatherald were right or not. One of the things my colleagues and I did in the 1990s was to interrogate Suki Manabe's prediction and look at satellite temperature measurements, which is what you see here. These are from these beautiful satellite-borne microwave sounders that measure the microwave emissions from oxygen molecules. Those emissions are proportional to the temperature of different broad layers of the atmosphere. By measuring at different microwave frequencies, you can back out the temperature of the troposphere, the mid-troposphere, the lower stratosphere, right up now into the upper stratosphere, about 50 kilometers above Earth's surface. These data, which we have now from 1979 through to the present, show exactly what Suki Manabe predicted: warming of the lower atmosphere, cooling of the upper atmosphere. And he was right. Even his simple model captured the basic physics of greenhouse gas increases. So this is just to illustrate that physicists Klaus Hasselmann and Suki Manabe really made fundamental contributions to our understanding of the reality and seriousness of human effects on climate. So the charge to the panel, this was, this is my final slide here. What can ICAM scientists do? What, from my perspective as a climate scientist, are the big problems on the horizon where the climate science community could really benefit from clever physicists' involvement? One of the problems that we've had for the last 50 years really is this uncertainty in so-called climate sensitivity. How much will the surface temperature of planet Earth increase for a doubling of atmospheric CO2? And that uncertainty largely arises from uncertainties in feedback mechanisms associated with water vapor, with clouds, with the optical properties, the location, the height, the amount of clouds, with snow, with sea ice, with the carbon cycle. And one of the key problems, if you're a policymaker, is knowing, is climate sensitivity on the low end of the current range, roughly 1.5 degrees Celsius for a doubling of CO2? Or, as newer climate models suggest, could it be as high as 5 degrees Celsius warming relative to pre-industrial for a doubling of atmospheric CO2? We urgently need to reduce that uncertainty. And many scientists think that there are clever transfer functions, things that we can measure and monitor in today's world that provide us with information about how these feedback mechanisms operate on short time scales, month to month, year to year, and that we can use that kind of information to constrain the uncertainty in the long-term behavior of the feedbacks over, say, the 21st century and beyond. A key problem. Another key problem is reducing the uncertainties in estimates of particulate pollution. Things like sulfate aerosol particles, black carbon particles, influence the reflectivity of clouds, cloud liquid water droplet sizes. We have clever satellite measurements now of many of these cloud optical properties, but we still struggle to optimally combine the latest, greatest satellite measurements with climate model representation of clouds in order to reduce uncertainty in the portrayal of clouds in climate models and better narrow that, that cloud feedback I mentioned up here. There's been a lot of discussion, particularly at agencies like the Department of Energy, in machine learning and AI techniques, and in trying to apply them to climate. I would argue this is another area where the physics community can really help climate scientists. But a key point here is that machine learning and AI are not an end in themselves. They should be used in order to address and help to solve key science problems. And one recent example of that is a paper that came out in Science Advances just a few months ago, where some scientists in Switzerland looked at very large collections of climate models that have large uncertainties in estimates of low frequency natural climate variability, and using machine learning and anchor regression and various other state-of-the-art statistical techniques, tried to address the question, does the uncertainty in climate model variability estimates affect our ability to identify human fingerprints on climate? And their answer was no. That to me, is the kind of contribution, the kind of marriage between physics, statistics, community, and climate science that we need going forward. I spoke a little bit, getting to the end, about satellite measurements of atmospheric temperature change. They're uncertain too. Even today, different groups arrive at different estimates of changes in atmospheric temperature because you have to adjust for things like satellite orbit drift, satellite altitude decay over the lifetime of a satellite, satellite calibration drift. And these are complex technical problems where climate scientists need help and expertise of folks in the physics and remote sensing communities in order to improve observational estimates of climate change. Finally, I think it's critically important to confront disinformation. And sadly, there are a couple of prominent physicists out there who have publicly stated on the record that climate science is an immature science, not of sufficient quality to warrant making any decisions on how to deal with human-caused climate change. I fundamentally disagree with that perspective, and often it's a perspective that's been articulated by people who have little familiarity with climate science. In my mind, going forward, getting a better dialogue with folks like that in the physics community is critically important. Maybe ICAM can play a role there. Thank you very much.
Thank you. Ben, these were all...
muted.
Oh, yes, I'm muted.
I'm sorry, Eli, do you want to take
Okay.
it?
Yes.
Excellent. So I took our marching orders slightly different. I will come in from a different angle from the other speakers. I already made references to my psychiatrist. I will make another one. He's an imaginary person, but nevertheless, around 2006, I was in a midlife crisis. I have been doing normal academic research like most people on this call. I was doing Anderson localization and high temperature superconductors and vortex state, but I was losing my motivation, and I really listened to many talks like Ben's about that the climate is the serious problem. The most serious problem the world is facing. Physicists, we think of us as possibly the best problem solvers on Earth. And I just asked myself the question, why shouldn't the smartest people work on the biggest problem? And I said, yes, we should. But my next question was how, given the fact that my training is in condo problems and the renormalization group, how can I possibly make an impact? I would like to therefore give you 5 examples where people with our kind of mainline academic physics research can have an adiabatic continuation towards problems which are really important for, if not directly for the climate change, but in my example, the renewable energy part of the climate challenge. The 5 points are, if you come from the world of strongly interacting electrons or perovskites, then this is an off-ramp for you because you can boost the efficiency of solar cells by boosting the energy conversion. If you have spent your time in academia studying the metal insulator transition, many of us do that, this knowledge can be imported into solar cells to make the charge extraction more efficient. Many of us, including Rajiv here, studied quantum glasses a lot. Well, if you have a background in quantum glassy dynamics, then there is a room for you in studying the performance degradation in the present world record holder silicon solar cells. Ben made a reference to artificial intelligence. If you have a background in artificial intelligence And if you don't, I guarantee that your students have, among students, artificial intelligence is very popular. There is a room for you in doing high precision modeling of silicon solar cell degradation. And finally, most of us grew up in renormalization group theory. You can contribute to build better magnets for hybrid cars. So let me jump in. If you come from strong interactions, then it's worth recalling that every solar cell on the face of the planet operates by the principle of one photon in, one electron out. However, about 15 or so years ago, people leaned heavily into a genuinely new paradigm that if there is a strong, if you can increase the Coulomb interaction in your solar cells, then one photon could produce more than one electrons. In particular, in comes the photon, photo excites an electron, but then this high energy electron then can transfer its energy to other electrons, excite them across the gap, and so you can have, one photon can generate multiple electrons. This sounded like a great idea. In 2004, it was shown. This is the quantum yield per photon, and in nanoparticle solar cells that people showed that you can produce more than one electron, and then people made genuine solar cells out of these. Okay, and so this is what strong strong interactions can do for you. And presently, the world record in perovskite quantum world record in quantum dot solar cells, like the ones where this happens, is 18%. If you know, most silicon solar cells are around like 21, 22%. 18% is a very impressive number. And also, if you like perovskites, because you studied high temperature superconductors, these materials have perovskite structure. Again, it's a natural off-ramp for you. Second, metal insulator transition. In these quantum dots, where the strong Coulomb interaction can generate a lot of electrons, it's a challenge to take the electrons out to the electrodes. Why? The electrons can need to hop from one quantum dot to the other. And so typically the electron mobility is low. But and the systems are in their insulating phase. And so people sought all kinds of ideas how to drive these quantum dot solar cells from their insulating state into the metal state. And this is a work from U of Penn, where they dispersed silver or gold particle quantum dots into the multiple exciton generating, electron generating lead selenide quantum dots. And once the golden nanoparticles percolated, the conductivity increased by 4 or 5 orders of magnitude. And this is the conductivity versus temperature curve. And this shows the very typical that for insulators, it goes one way, for metals, it goes the other way. So your expertise in metal insulator transitions can be very important, increasing the transport in these quantum dot solar cells. This is a recent paper of ours where on the electron density disorder plane, we generated the phase diagram of these systems. Third, if you do quantum glasses, then again, there is room for you. The present world record holders among silicon solar cells, we cannot beat Eli's wonderful gallium arsenide solar cells, but we can come close. The world record efficiency is around 27%. But one of the reasons, not the only, but one of the reasons why they are not accepted by the market is because they show a unnervingly fast degradation of their performance. Okay, and so we set out and studied how does this degradation take place, and we looked at it as a glass problem. We determined the barriers which control the degradation. We created the distribution of these barriers, and then we simulated in an accelerated Monte Carlo the defect generation, the defects which lead to degradation. And here is their time dependence. We were able to connect 24 orders of magnitude in time scales. So that was very useful. And we also discovered a scaling law. I don't know where to put this thing. A scaling law that if you want to study degradation, you cannot wait for 10 years, which is the lifetime of a solar cell. But if you increase the temperature of your solar cell, you figure that you are simulating faster degradation. But what is the relationship, the quantitative relationship? And we found a scaling form between the degradation at normal temperatures and acceleration temperatures. And look at this. There is an power law form where the exponent, we predicted the exponent, and the exponent fit the data perfectly, and the exponent is a ratio of temperatures. It was very nice. So you can make, starting from quantum glassy dynamics, you can end up with accelerated testing scaling forms, which we really hope the industry will in fact accept. Next, artificial intelligence. I told you in the previous slide that the problem is that there is a degradation taking place and defects are being formed. But how are these formed? And we didn't know. Very recently, we just published this, or sent out this, submitted this paper recently. The regular simulation techniques do not have enough precision to study what happens in these amorphous crystalline silicon interfaces. So we developed, we used machine learning and trained our molecular dynamic simulation over 27 rounds of very painstaking training rounds, so that we were able to reproduce DFT results within a very remarkable 4 milli-electron volt precision. So we made molecular dynamics reach the precision of density functional theory, except that molecular dynamics scales with n to the first, while density functional scales with n to the third. So we are capable of simulating cells of like 5,000 silicon atoms, which is totally out of the realm of possibilities for density functional theories. And we found the dashed line. This is the model. The dashed line is where the interface is between crystalline and amorphous silicon. And we found that the potential felt by the hydrogen in these solar cells is really feeling a tilted potential. The structure of the solar cells is driving the hydrogens away from the interface. This depassivates the interface. This is the generation mechanism for defects. And then with some graduate students, some of them are on this call, we found a way to come up with a very simple proposition to the silicon solar cell industry to change a deposition protocol that reverses this driving force and actually pins the hydrogen to the interface. This preserves the passivation. All this became possible because we used artificial intelligence to do an unprecedentedly high precision modeling. And the last thing is, and I know the last minute, 12 years ago, Toyota Corporation called me that they are building the Prius. The Prius is an electromotor. It has a good magnet. It needs better magnet. Can I help? And I said, yes, I can do a finite element modeling of magnets. And so we started modeling the magnets. But one of the things what we stumbled upon repeatedly, that our simulation results depended on the mesh size, what size mesh you use here. That's completely an artifact. And so we struggled how reliable are our predictions. And the solution again comes from academic science. I remember my training about renormalization group, and I said, hey, wait a minute, for the individual cells, people just use normal standard magnetization data. And I said, that's no good. The renormalization group tells us that there are fluctuations inside these finite elements, and those need to be taken into consideration. And so here is the data of the mesh size dependence of some quantity without scaling, and here it is with scaling. So again, an academic science idea of renormalization group was able to make a previously somewhat sketchy simulation technique and make it reliable by eliminating a substantial artifact. And I'm happy to say that Toyota Corporation in 2018 started to put the magnets which we developed, in collaboration with other invited researchers, into their Prius machines. So I just wanted to make this point that we don't need to only yearn. People with skill set like those who are sitting on this call in strong interaction electrons, metal insulator transition, quantum glasses, artificial intelligence, or renormalization group can directly export their knowledge to challenges in the field of renewable energy. And I hope that this can serve as a motivation and an enabling off-ramp for all of you. That was my presentation, and I would be very happy to open the panel for discussion.
Gergely, congratulations on these wonderful applications, and it is a great example to students. The world changes, and you can produce that change yourself through your research. So that's really terrific. The other thing I'd like to mention is I'm not an expert in agriculture. So in fact, I'm closer to the solar cells that you talked about. And how did it happen that I became so interested in agriculture? So I started in solar cells 42 years ago. And the company had a consultant whose name was Al Rose. And probably none of you have heard of Al Rose, but Al Rose created the first television camera and was used in all television from 1940 to 1980 until the CCDs took over. And so I was working on solar cells, and Al said, you know, you should look up the energy content of corn, because oil, it was the second energy crisis. Oil had become very expensive. And there wasn't as big a difference between the energy price of corn versus the energy price of oil. And I developed a real appreciation for agriculture there.
So Ben, maybe you want to address Eli's question to you?
You know, I'm not really knowledgeable about the solutions side of things. I wish I was. My expertise is limited to the physical climate system. That said, I think for the kind of solutions that Eli discussed, climate models might be useful at looking at some of the implications of those solutions. So you can, in climate model world, change the land surface properties according to how you think things might change in terms of surface roughness, albedo, all that kind of stuff. If you converted large areas of land into these storage sites for dry agro waste, and you could look at the implications of those changes in surface energy fluxes, in surface roughness and surface albedo for local and regional climate. So that would be something where there might be an interaction term between what Eli is proposing in the world of climate modeling.
Awesome. Questions from the audience?
Thinking.
I don't see any hands.
So are we left to discuss among ourselves?
Maybe I can ask a question to Eli. Clearly, we all agree that the energy density in the covalent bond is huge, and we need to use that if we're going to have any applications that such as airplanes that require high energy density. We're never going to get the energy density out of conventional or even very improved electrical batteries. But your suggestion is predicated on the idea that that we won't solve that problem. And presumably one direction is to find new ways to convert solar power into hydrocarbons or into hydrogen, I guess, is the alternative. Why do you rule that out, or do you just see using agro sequestration as a complementary approach?
Well, I think I had a slide that sort of said that we have to do everything. I've done a lot of research on solar cells. I started a solar cell company. So I really believe we're going to see a lot of improvements of technology. And that's what we heard from Gergely in his talk, is all the ways in which we can improve technology to lessen the carbon dioxide burden. But to provide real security to humanity, my belief is you need to have a practical way to extract carbon dioxide from the atmosphere, so that people can rest easy. They're very worried right now, and we need to assure people that there are solutions that are actually very reasonable.
Good. I have a question to Ben. Ben, one thing what really I think is really exciting, potentially exciting for an academic researcher, the need to match many different scales in climate modeling. You have to model like individual snowflake formation to understand individual clouds. There are many clouds. How can you capture them on even bigger scales? Can you talk about the scientific challenges of connecting really atomistic scale knowledge onto planetary scale predictions?
Great question. And I think there is some progress being made in terms of clouds. For example, the way the field is going is towards cloud resolving models that can, over some smaller domains, or now even globally, resolve the effects of clouds explicitly, rather than parameterizing the average impact of clouds over some grid box. So that's big, but the computational demand goes up. And of course, as we make these Earth system models more complex and include finer horizontal scales and more vertical levels in the atmosphere and the ocean and biogeochemistry and atmospheric chemistry, which is computationally expensive, the challenge is to run a model like that for simulations that enable you to compare with observations over seasons, over a year, to look at interannual variability. And that's still a challenge for us, that as we increase the complexity and we increase the resolution in space and in time, it becomes more difficult to extract meaning from these very, very large simulated climate data sets and compare them with observations to figure out how well we're doing. So I think that's an area where we need help in the climate community. We're generating more data than we can usefully extract meaning from.
Awesome. Dan has his question up, his hand up.
And I think this will probably have to be our last question because we're running over time. Yep.
Okay, Dan. Just
I was wondering if Dr. Santer could you mentioned climate sensitivity. I'm wondering if there are any simple physicist arguments that can that could that could be brought to bear here, because I mean the naive picture clearly doesn't work. I mean in that, from what I understand, there's like 340 watts per meter squared of solar radiation that we get on average, and when you deal with the clouds and the albedo, maybe that leaves about 240. And from what I remember, my Scripps colleague Jeff Severinghouse telling me was that the Earth's energy budget is such that we're getting about an extra, we're getting in the net like 241 and putting out 240. But if I take the ratio of 241 over 240 and raise it to the 1/4 power, I mean, some very crude, calculation, and you get a very small fractional change in terms of what you'd expect in terms of the mean surface temperature of the Earth. So clearly that argument is totally wrong. What is it? Just way too complicated to explain a back of the envelope calculation for what we should expect for change in the average surface temperature given the imbalance in the energy budget?
Well, I'm not entirely sure I answer your question. I understood your question, but here's a stab at an answer. One is that scientists have actually measured the energy perturbation both at the top of the atmosphere and at the Earth's surface associated with human-caused CO2 increases. So we can measure the changes in long-wave and short-wave radiation at the surface, at the top of the atmosphere, and see whether those measured changes are in accord with basic theory and with model calculations. And they are. Those energy imbalances can't be explained by natural causes alone. Changes in the sun's energy output, volcanoes, internal variability, you name it. So that's good. It's sort of in energy balance, a direct confirmation of human-caused changes in atmospheric CO2 levels. Now, the problem, as I mentioned, is if you want to constrain uncertainties in climate sensitivity, which are currently about a factor of 3 from 1.5 degrees Celsius warming of the average temperature of the Earth to over 5 for a doubling of CO2, you've really got to constrain uncertainties in these feedbacks. And those are primarily feedbacks associated with clouds, the most uncertain, water vapor, snow, and sea ice. And that's, I think, where we need a lot of help from the physicists to look for timescale invariance. So there are aspects of these feedbacks that we can monitor and observe on daily timescales, on monthly timescales, on interannual timescales. And there's no evidence from the model simulations that the feedbacks are timescale variable, that they change fundamentally as you go from shorter to longer timescales. And that raises the possibility of using observable behavior of these feedbacks to constrain long-term uncertainty. That's, I think, where physicists could help us in climate science.
Excellent. I listened to Piers mention that we should really observe the time. So I take this opportunity to thank the two wonderful participants in the panel, Ben and Eli. Thank you very much. And
thank you so much.
Thank you.
Thank you.